All right, everybody, welcome back. We ended the previous lecture by talking about momentum conservation and by looking at the differential form of the momentum equation and the pressure energy equation, we came up with this relationship between the friction and entropy of production. And we also talked about conservation of energy and other quantities using the Reynolds transport theorem. Today what we're going to do is we're actually going to go ahead and start to talk about compressible flow. However, before we do that, we need to talk about a very important concept, which has to do with the stagnation state. And this is something that we'll be using constantly for the rest of the course. So make sure you read about this concept very carefully in your textbook and follow along very closely during the lecture. Okay? So let's go ahead and get started about stagnation, which, like I said, is a very important concept. Okay, so I'm just going to go ahead and write down the definition to start, and then we'll proceed from there. So the stagnation state is a reference state defined as the thermodynamic, which I'll abbreviate TD, state, which would exist if the fluid were brought to V, or flow velocity, equal to 0, and Z equals 0, so therefore like zero potential. Without energy exchange, so therefore, no heat or work done, and without any losses. Meaning we have dSi, which we discussed in the last lecture, is equal to 0. And this actually implies, since there is no heat transfer, and since dSi is equal to 0, this implies that we have an isentropic process here. Okay, so stated simply, the stagnation state is the reference state, which would exist if the fluid were brought to V equals 0 and Z equals 0 through an isentropic process. Okay? So let's go ahead and highlight these guys and proceed. So let's take a look at that energy equation for 1D steady flow between points A and B. We derived this during the previous lecture. So consider the energy equation for 1D steady flow. Oops. Between points A and B. So we have HA plus VA squared over 2 plus GZA is equal, or drop the Q there, plus Q is equal to HB plus VB squared over 2 plus GZB plus Ws. Okay, so this is the equation, the energy equation that we derived before. Now we're going to come up with an expression for the stagnation enthalpy. Okay, so we're going to let B be, is we're going to let B be the stagnation state. So what that means is that Q and Ws and VB and ZB are all going to go to 0. And we can write it as, now, one point that I actually need to make here. So this is the stagnation state. We're calling it the stagnation state. And I should have continued to say it's the stagnation state corresponding to the static state A. So this is the stagnation state corresponding to the static state A. And static, what we mean by that is that is the state from the reference of traveling with the fluid. Okay, so B is the stagnation state corresponding to the static state, A, and the reason why those are linked is because B is the state that you would reach starting from A if you went along an isentropic path. Okay, that path is unique starting from A, and so you travel along that isentropic path until you have 0 potential and 0 flow velocity, and then you've reached the stagnation state that corresponds to state A. Okay, that's why it was important that I make that note that B is the stagnation state corresponding to the static state A. Okay, and so what we do is, in this case, we can rewrite what HB is, and in fact what we're going to do is we're just going to name that HTA. Okay, the T stands for stagnation, and then the A is saying that it's the stagnation state corresponding to the static state A. So HTA is equal to HA plus VA squared over 2 plus GZA. Okay, and this is super important, this formula right here. So we'll go ahead and frame it. And what this is called, this is the stagnation enthalpy, or it's also called the total enthalpy. And that's where the little T subscript comes from, corresponding to state A. To state A. Okay? So total enthalpy, stagnation enthalpy, this is the definition. For gases, which is in most cases what we're going to be dealing with, the mass is negligible, and so potential differences are not important. And so typically we just write that the total enthalpy or the stagnation enthalpy is equal to the static enthalpy plus V squared over 2. Okay? So most of the time you're going to be dealing with that equation, as opposed to the one above with the gravitational potential considered. Okay, now here's one of the most important facts that you will use over and over again in this course, is that in an adiabatic system with no work, the stagnation enthalpy remains constant. Okay, very important. So the reason why we know that is because, look, if you look at the, consider the energy equation. energy equation between points A and B. We can just do A and B again. So HA plus VA squared over 2 plus GZA plus Q is equal to HB plus VB squared over 2 plus GZB plus WS. Okay, we have no heat, so it's adiabatic, no work, and you can see that what we have here is that HTA is equivalent to HTB, right? Because what's left over after you cross out the heat and the work is the definition of the total enthalpy corresponding to that state. Okay, so we can see that in this case we can just sort of define a total enthalpy, and it's the same between points A and B. Okay, so you're going to see that this relationship, this realization that as long as you have adiabatic flow and no work, that you have this stagnation enthalpy being constant, we're going to use that really so often it'll be burned into your brain. Okay. So let's continue developing the stagnation state concept, okay, and we'll draw some diagrams as well. So let's start with the stagnation pressure energy equation. Okay, make this a section here, and then also I should have made this a section as well. The green highlighter. Okay, so let's draw a figure that kind of gives you an idea of the topology of the processes that we're dealing with here. So let's draw an HS diagram. So we're plotting the enthalpy as a function of S. Okay, and we have some sort of process that's making its way through this diagram in this direction, and we have two states. One is here, and then one is here. Actually, I'm going to move that one over a little bit so that there's a little bit more of a change. Okay, so let's make this clear. Go straight down there. Okay, and so this is state 1, and this is state 2. Okay, and then we have some change in entropy between state 1 and state 2. Now, the stagnation state is going to be at some point above here. So let's say that it's right here, right? So this is actually 1t. And we traveled along a so-called isentrope, right, to state 1t. And then let's presume that the process from state 1 to 2 is both adiabatic and doesn't have work, so that the stagnation enthalpy remains constant, and therefore the second stagnation state will be there, the same value of enthalpy here, okay, and so that's the general diagram there. So you can see that to go from state 1 to state 1t, we moved along an isentrope, or along a line of constant entropy, or constant S, okay? So graphically, that's what's going on there. And we had a change in entropy between state 1 and 2, but because it's a no work, no heat transfer process, we have the same stagnation enthalpy. It's also worth noting here that since we have a change in entropy at all, we must be having some sort of irreversible enthalpy, or sorry, irreversible entropy production. Okay. So let's go ahead and do a little bit of analysis here. I'd rather use black. So we will begin with TDS is equal to DH minus VDP. Okay, remember I should use a lowercase s here. So remember this is just the fundamental thermodynamic relation with the definition of enthalpy subbed in for U, for du rather. Okay, so we have that, and we want to make the note that stagnation states are legitimate thermodynamic states, even though they don't actually exist, right? So they're just reference states, but we can manipulate them and work with them as if they're real thermodynamic states. So I can write down TT DST is equal to DH sub T minus V sub T dP sub T. So it's like the same relation for the stagnation state. Okay. So then we have that ds is equal to dst. Right? So why we're talking about the stagnation states between, say, state 1 and state 2, why is the change in entropy between state 1 and state 2 the same as the change in entropy between the stagnation states? Well, it's because, so why is this true? It's because the transition from state 1 to state 1t and the transition from state 2 to state 2t, they are isentropic, right? So that is why we have ds being equal to dst. Okay, so let's go ahead and continue. In fact, we'll use this fact. So we know that ds is equal to ds E plus dsi, okay, which that irreversible production. And if we sub that in, we can see that we have T sub T, the stagnation temperature, times dse plus dsi. So we've subbed in the total ds into the stagnation enthalpy thermodynamic relation on the top right there. And we set that equal to the right-hand side of the equation, dht minus vt dp sub t. Okay? Now, last time, we showed that for steady 1D flow, we have that delta Q is equal to delta Ws plus dH plus dV squared over 2 plus G dZ. So that was the differential form of the energy equation. And so we can actually see that this part here, I'm going to put a little under bracket, you can see that is actually just the total differential operator applied to the stagnation enthalpy, right? Because that's the definition of the stagnation enthalpy, that H plus V squared over 2 plus GZ. Okay, so we can actually rewrite the right-hand side of the equation as delta Ws plus dHT. And then we can solve for dHT in terms of the work and T dSE. Let me make sure I'm keeping all the lowercase and uppercase going here. So dSE minus delta Ws. So what's happening here? Where does the TdSE come from? Remember that this is just equivalent to delta Q, right? That was from our thermodynamics lecture. Okay, so now we have this expression for dHT, and we have this relationship on the top right here after we noted that ds was equal to dst. And so let's sub everything in. We have T, stagnation of the temperatures, T sub T, dSE plus dSi is equal to T dSE, this is subbing in for dHT, minus delta Ws minus V T dPT. Okay, and then we'll change the specific volume, bring the density out, and we'll move everything to one side of the equation, and what we end up with is what is called the stagnation pressure energy equation. So dPT over rho T, that's just the definition of VT, plus dSE, sorry, I'm having a hard time writing lowercase s's. dSE times quantity Tt minus T, the difference between the stagnation and static temperatures, plus the stagnation temperature times the incremental change and irreversible entropy produced, plus delta Ws is equal to 0. Okay, so this is another one of our equations that we can use to reason about our thermodynamic systems. And like I said, this is called the stagnation pressure energy equation. Okay? So now let's look at this equation in the case where there's no heat. Consider the case, the case where delta Q is equal to 0, delta S is equal to 0, and dSi is equal to 0. So that's like saying no losses. So if we look at that case, this tells us that dPT over rho T is equal to 0, right? Because dSE is equal to 0 when delta Q is equal to 0. The work term goes away, and we have no losses. And what this tells us is that the stagnation pressure is constant in this case. Hugely useful analytical tool. Okay, so if we assume no losses and there's no heat transfer, essentially, if between two states in your system you have isentropic flow without any work going on, then you can assume that the stagnation pressure is constant. Okay, and again, this will become really important, like when you're analyzing a propulsion system, to know the regions in the propulsion system where the stagnation pressure remains constant is really a huge part of the analysis there. Okay, so now, of course, in reality, this doesn't actually hold. Okay, so you can have systems that are approximately adiabatic, like there's no heat transfer happening, and have no shaft work. But you will often always have some amount of irreversible losses, right? So in that case, so let's say in reality, there are always losses. Now they may be small, so that we can kind of assume that they don't exist to make analysis easier. But in reality, there are always losses, and so what we're left with in that case is that dPT over rho T plus the stagnation temperature times dSi is equal to 0, right? So from here you can see that that losses cause the stagnation pressure to drop. Okay, which is an important thing to know in your head. If you have losses going on, you're going to have a stagnation pressure drop. Okay, but what this allows us to do is we can rewrite this, say, by using the ideal gas law, where we say rho T is equal to PT over RTT. Okay, we can rewrite this equation in the following form. We have dPT over PT is equal to dSI over R. Okay, because the stagnation temperature cancels out. Okay, and this, if we can solve this, you can integrate this and get the following relationship, which is PT2 over PT1 is equal to E raised to the negative delta S over R. Okay? Another very important relationship. Okay, so you can solve for the precise increase or decrease in stagnation pressure depending on the entropy change in a more realistic channel, but still in a case where there's no heat transfer and or shaft work. Okay. All right. So that's good. So that sort of concludes our discussion of the stagnation reference state. We'll come back to this literally countless times. This is really important for most of the analyses that we'll do. Okay, but now let's transition to really getting into the compressible flow topic by talking about the sonic speed. Okay, or in other words, the speed of sound. Or in other words, the speed at which information travels through a medium. Sonic speed. Okay, so, I often, if I'm teaching this in person, I will often tell the students to, I'll ask them a series of questions like, what is the sound wave? What's actually happening? Describe the motion of the air molecules, right? What's happening in their head when they think of a sound wave propagating? So I'll try to draw this for you to give you an idea of what's going on. So like maybe I'll just write down sort of like, what are sound waves? Is the question. Okay, imagine we have some sort of like impulse. Like I'll just draw kind of a little drum thing here. Like we'll make it a little tambourine. And what happens is, this is at time equals 1. And what we're going to plot underneath here is the pressure as a function of space at that time. Okay? And what it looks like, say if you had one sharp impulse from a drum of some kind or something like that, there's this drop in pressure and then an increase in pressure. Okay, that's like the peak of the sound wave or the impulse, and then it goes back to this quiescent level, and that's sort of like P ambient. Okay, the ambient pressure, and then this thing is called a rarefaction. And in one dimension, what this looks like is the air molecules become all bunched up around the peak. That's like a increase in pressure, and they're spread out behind the peak. And then ahead of the peak, they're kind of uniformly spread out. They're quiescent. They're just chilling. Okay, and so at a later time, the disturbance propagates further downstream. So still plotting pressure versus distance here. And we have quiescent then the rarefaction, the peak, and then back to quiescent here. And then here you have the pileup, the uniformity here, and then uniformity upstream. Okay? And so on, right? Like if we just drew this again, you're going to have some. Sorry, I didn't draw the rarefaction. You're going to have the same sort of structure is propagating forward in time, okay, and the pileup is happening further downstream. Okay, this would be like T3. All right, so this you can think of this as it's a single impulse, but you can think of this as one crest of a sound wave. Okay, you know, in reality, a sort of constant sound is a bunch of these vibrations traveling through space. Okay, so all right, so a couple of things to note here. The molecules, the air molecules, are actually moving along the axis of travel. Okay, this isn't like an electromagnetic wave where the E field is flipping up and down, say, and the wave is traveling to the right on your screen, right? What's it might be the left on your screen, but in this case, the molecules travel along the axis of travel. And that makes this a sound. That makes sound a longitudinal wave. Sound is what's called a longitudinal wave. Okay. Like I said, the opposite would be called a transverse wave, which is like electromagnetic wave or waves at the top of a pond, right? The surface of the pond is moving up and down, but the waves are traveling across the surface. Okay, so hopefully that little discussion there gives you an idea of kind of what's happening in a sound wave. It's these local compressions of the air molecules to higher pressure that propagate through the action of the molecules actually interacting with each other through collisions. Okay. So let's derive the speed of sound here. Say, let's derive the speed of sound. Okay, so what we have to do is we have to sort of reduce this picture above, which is already in one dimension, to be even more bare bones. Okay, so what we want to do is we just want to have a traveling disturbance in an infinitely long pipe or channel with air. Okay. And some cross-sectional area AC. Okay. So let's go ahead and draw that. And let's say that we have, like I said, this infinitely long pipe or channel, and it goes on forever in both directions. And we have this disturbance. Okay. And the disturbance is traveling at some speed A. Now, upstream, the field is quiescent, so you just have some pressure and density that's nominal, okay? And then once the disturbance passes through, there's some compression, some small increments or change in the pressure and density, so that sort of downstream of the disturbance, you have P plus delta P and rho plus delta rho, okay? So it's some incremental change. All right, and so we are going to assume no losses. So the disturbance propagates unmitigated. and we're able to assume that in concert with that assumption, that basically implies that the speed is constant, right? Because the channel is infinitely long; it's not changing as a function of distance or propagation distance. And so if the disturbance is propagating unmitigated, there's no sort of energy ejection happening here. The disturbance is going to propagate at a constant speed. So that's why we just set it to a constant speed A. Okay, so now to proceed, let's fix our reference frame. Fix our reference frame to the traveling disturbance. And we're going to wrap it in a very tight-fitting control volume to make the problem into a steady state problem, right? If we're walking from the lab frame and we can see the disturbance moving, it's not a steady problem. But if we fix ourselves to that disturbance, since the channel is infinite in both directions, it looks like a totally steady state problem. Okay, fix reference frame is traveling disturbance. Use tight fitting CV. And then this makes our problem steady state. Steady state. Okay, so let's go ahead and draw that situation. So now we're zooming in. We have the disturbance, and then we draw our control volume around this disturbance, and presume this is very tight fitting. It's just right around the edge of the disturbance. And then the left-hand side of the, we'll say that this is the x-axis, say. The left-hand side of the control volume, we'll call that state 1, and then the right-hand side, we'll call that state 2. Okay? And like we said, this disturbance now appears to be stationary. Okay. So now what has this done to the upstream and downstream fluid properties? So the question becomes, does the reference frame, does that actually affect what the static pressure is? Okay, the pressure as measured by some sort of pressure probe. And the truth is, and the answer to that is no, it doesn't, because in any sort of property that you call static shouldn't be affected by its value shouldn't be affected by changing the reference frame. Okay, so the pressure upstream and downstream of the disturbance in this new reference frame are the same as they were before. So we still have rho plus delta rho for rho 1, and then P2 is still the quiescent flow P, and rho 2 is still the quiescent flow rho. Okay, but the fluid velocity did change, right? So downstream of the disturbance, we still had an increment in fluid velocity from the quiescent flow, some small change. But now it's being boosted by the speed of the disturbance A. And then the upstream fluid velocity, it used to be quiescent at completely zero velocity, but now it's traveling at us in the negative x direction at the speed minus A. Okay? So speed A in the negative x direction, so therefore the overall velocity is negative A. So, okay, so let's go ahead and get started by looking at continuity, right? In general, in these types of analysis, any sort of fluid mechanics analysis, it's always good to start with the continuity equation or mass conservation in general. It's a nice it's a nice starting point that usually gives you a relation that allows you to simplify things later. Okay, so the flow is 1D. So normally, let's just write down the whole sort of Reynolds transport theorem for mass. So we know that the left-hand side goes to 0 because we're not relativistic, the mass isn't changing. And then we have this, rho times v dot n hat dA, right? And we actually have already done this. First of all, it's steady state, so this term goes to 0. And then the right-hand term, we've basically shown that collapses to, when we do this 1D steady approximation, we just get that the mass flow rate out is equal to the mass flow rate in. Okay, and we showed that in the last lecture. Okay, so then let's go ahead and write that out in terms of the densities and the cross-sectional area, which is not changing, right? So we have rho 1 A1 V1 is equal to rho 2 A2 V2, and like I said, the cross-sectional area is not changing, so A1 is equal to V1. And then let's go ahead and sub in what our properties are at each of those points. So on the left-hand side, we have P plus delta P times dV, or I should really write it as delta V minus A, okay? And that is equal to rho minus rho times A. Okay? So let's go ahead and FOIL the left-hand side, write all the cross terms. So we have P times delta V minus A times, sorry, this is rho, not P. These are all rhos. So rho times delta V minus A times rho plus delta rho times delta V minus A times delta rho is equal to minus rho A. Okay, so that term's going to cancel from both sides. And then also, we're going to notice that, okay, so these small increments we said at the beginning, we're assuming it's like infinitesimal, right? And so two infinitesimal things multiplied by each other, they're going to be much, much smaller than sort of a macroscopic quantity multiplied by an infinitesimal. So that term is actually much smaller than the other terms in the relationship, right, or the equation, right? So we can just say that this is basically something like something tiny times something tiny. That's equivalent. That's very, very close to being equal to 0. So that's why we cross that term out as well. It's like a second order term. Okay. So then what we end up with is that the increment in flow velocity across the disturbance is equal to A over rho times the increment in rho. Okay. So nice. So we'll sit there for a second. So this is what we got from mass conservation, right? We started with continuity, and that's the sort of, we're able to solve for what the increment in velocity is in terms of the other increment, the increment in density. Okay, so we'll set that aside for a moment. The next thing that we want to do is we want to do momentum conservation across the disturbance. Okay, so because we made, specifically because we made the CV very tight fitting to the disturbance, that allows us to ignore the friction forces on the top and bottom of the control volume. So we'll go ahead and write that down. Since CV is tight, ignore any sort of shear wall force or any sort of force of friction. Okay, and so then let's go to the Reynolds transport theorem, and we'll look at momentum conservation specifically in the x direction, since this is a 1D problem. So on the left-hand side, we'd have the sum of the forces, okay? And then we have d by dt of the integral of rho vx, so the velocity in the x direction, times v dv, plus cs rho vx times v dot d dot n hat dA. Okay, and we know that on either side of the control volume, v dot dn is going to be either plus or minus vx, right? Because we have an outward normal, and yeah. So we'll have to be careful about, of course, about our reference frame here. Make sure we get all the signs right. So what are the sum of forces on the left-hand side of the equation here? Well, since there's no shear forces or friction forces, we only have to worry about the pressure. Okay. So on the left-hand side of the control volume, we have the pressure acting in the positive direction, which would be P plus delta P, that quantity times the cross-sectional area, minus P times the cross-sectional area, right? It doesn't need to be in parentheses. Okay, so that's the whole left-hand side. And then we also know that we're steady state, so this whole term goes to 0 again, and then we're only concerned with momentum transfer in and out. So what's the density at the left-hand side? The density on the left-hand side, we have rho plus delta rho. And then the velocity on the left-hand side is delta v minus a. Okay? And then we also have another delta v minus a times the cross-sectional area. So the issue here is, what do we do with this sign, right? So the flow is traveling into the control volume in the positive x direction. Say we're taking the x to be positive, and then the outward normal on the left-hand side is pointing outward, so they're anti-aligned, and so you're going to pick up a negative sign in front of this. Okay, and then we add to that rho times minus a times minus a times a. Okay, so the cross-sectional area appears in all these terms, so we can go ahead and cancel that. And then we can, once we cancel that on the left-hand side, we're going to see that these two pressures are going to cancel each other. And we'll get an expression for delta P, which is minus rho times minus A times delta V minus A plus rho A squared. Okay, so you can see that there's a rho A squared term that will be negative here. That's going to cancel with that. And what we end up with is that delta P is equal to rho A times delta V. Or in other words, we found another expression for delta V, which is delta P over rho A. Okay, so that's the relationship that we got from applying momentum conservation. Okay, so then let's combine these. Okay, so we have two different expressions for delta V. Let's set them equal to one another. And in other words, we're putting the continuity and momentum conservation together, and that tells us that delta P over rho A over, okay, come on, here we go, over rho A is equal to A over rho delta rho, right? Or rearranged, it's that delta P over delta rho is equal to A squared. Okay, so then let's go ahead and take this to the limit to make it a proper derivative. And we will say that we have partial P, partial rho, holding something constant here, is equal to A squared. Okay, so let's say we're taking the limit. Here, there's some heavy hand waving happening there, and then we have this partial derivative of P with respect to the density, holding something constant, is A squared, and so what do we have here? Well, we know that there's no heat transfer happening, and then the one thing that we need to assume here is that all the collisions of the air molecules are elastic, meaning that they don't have any losses associated with them. And we already were assuming that no losses were occurring. And so since we're making that assumption, what's actually being held constant in this partial derivative here is S, or the entropy. Okay? So that's actually your definition of the sound speed. Okay, it's the partial derivative of the pressure with respect to the density holding entropy constant. Okay, so now let's bring this back to materials that we're interested in. So what's the So what is the relationship of the pressure and the density for an isentropic process for an ideal gas? So let's write that down a little bit more clearly. So for an ideal gas, what is true of the pressure and density for an isentropic process? And this is where you need to go back and look at the polytropic process relationship, right? So in a polytropic process, we showed that P times V raised to some power is a constant for a polytropic process, and that power for an isentropic process is gamma, or the ratio of specific heats. So what we have here is that PV to the gamma is constant, right? And V, in this case, is just 1 over rho. So what we have is that we can write down P is equal to rho raised to the gamma times some constant, right? All right, so that's one of the key insights here. And then we can actually compute this derivative of P in this constant entropy case. So we want to take the partial derivative of P with respect to rho at constant entropy. And what that's going to be is we can just take this relationship that we just developed on the right-hand side. So that's equal to gamma times rho to the gamma minus 1 times that constant, right? This is the same as we can resubstitute P into this. So here we end up with gamma times rho to the gamma minus 1. And then we substituted in for the constant, which is just P over rho to the gamma. And so what that's equal to is gamma times P over rho. And then if we use the ideal gas law, we end up with gamma RT. Okay? And so therefore, for a perfect gas, we know that the sonic speed is equal to the square root of gamma RT. Okay? So I'm going to write that down. Sonic speed of a perfect gas. Okay? So in general, this is sort of a function of the gas type, because R is a function of the gas type, and the temperature. Okay? So always keep that in mind. All right, so now that we are equipped with a sonic speed here that we've derived, let's actually revisit this topic that we touched on in the very first lecture, which is the Mach number. Okay, so we've already stated this, but the Mach number is defined as the velocity, the speed of the medium, divided by the sonic speed of the medium. Okay, and in general, these are both local quantities. Okay, we know that if m is less than 1, that's subsonic. If m is greater than 1, supersonic. And then I've said this, I might have said this before, but it's worth writing down. The Mach number is the most important parameter in the analysis of compressible flow. Okay? So let's sort of develop these ideas of an object or flow traveling faster than the speed of sound in the medium. What I want you to do is imagine a point in a fluid that emits one disturbance per second. One disturbance per second. Okay, so pictorially, what we have here is this point at t equals 0, and then at t equals 1, it has this disturbance front that it's emitted, and the distance between the point and that front is a, okay? And then at a later time, say t equals 2, it has another new ring of disturbance front, and then the initial disturbance that it emitted is now out here. Okay? So essentially what you're going to end up with is a bunch of concentric circles that represent the disturbance front. So now going out to here is 2a, and then to here is just a. Okay? And then so on as you get to later times. So, and here's where I'm going to do my best to try and draw these pictures here. So now let's go ahead, allow the disturbance to move at v equals a over 2. Okay, and it actually might be helpful to put some grid lines on here so I can draw this more accurately. Okay, so what I mean by that is, let's say that we have the disturbance at time 0, and then it moves a over 2 over, and then it moves a over 2, so sort of each of these grid points is representing moving a over 2 distance and t equals 1 second or whatever. Okay, so this would be t equals 0, t equals 1, t equals 2, and t equals 3. Okay, and so what's happening here? So t equals 3, and that's the current time. Okay, so it doesn't have any sort of ring around it, right? But then at t equals 2, which is 1 second ago, it emitted a disturbance that, here we're going to have to move this around here, actually, because these circles are going to be bigger than I anticipated. So let's draw the disturbance that it emitted at t equals 2, or rather 1 second ago. Okay. So this disturbance front is centered at t equals 1, and then we have another disturbance front that'll be centered at t equals 0 that's even larger. Let's draw these lines here. This line is 3a in length. This line is 2a in length. This line is 1a in length. And then the t equals 3 point is emitting right at the current time, okay? So you can see how the disturbances are propagating in space. Okay? Now, let's imagine that we have the disturbance move at v equals a. So next, move at v equals a. So now the disturbance is doing this. Okay, so it's starting at t equals 0 here, and it's moving a full t equals 1, t equals 2, and t equals 3. So it's moving a full sort of a distance in every second. Okay, and so the first the disturbance that it emitted at t equals 2 is there. Okay, and then the disturbance that it emitted at t equals 1 is going to be okay. All right, so apologies. This is it's better to have the cleaner circles than to try to draw them myself, to be honest. So okay, so when v is equal to a, you can see that all the disturbances are sort of piling up at the location that the point is when it gets there, right? So in this case, when v equals a, we actually have this line here. And we can basically say that nothing, let me get the zoom worked out here. It's a little. So in this case, nothing ahead of the object is forewarned of its approach. Oops. Okay, so the way that you could you would be warned of the object approaching is by the disturbances that it's emitting reaching you before the object reaches you. But in this case, the object is traveling as fast as the disturbances that it's emitting, and so you can see they're kind of just piling up where the object is. Okay, so finally, the last thing that we want to do is we want to visualize the case where v is equal to 2a. Okay, so now the disturbance is traveling at twice the sonic speed. And so okay, so this is interesting, right? So what we can do is we can draw a line actually that connects the sort of furthest extent that the disturbances have reached spatially. Okay, so if I just draw a nice clean line from along this spot here that intersects with all of the, let's go small eraser, stroke eraser, so not overlapping stuff, and then draw another line. Starts there and goes this way. Okay, so that line represents the furthest extent that the disturbance is emitted by the particles have traveled. And we can see that here, what we'll call on this side of the line, on the inside, we'll say that this is the zone of action. Here, let me get the zoom right again. So on the inside of the line, this is called the zone of action. And then the outside of the line, this is the zone of silence. And the reason why it's called that is because none of the disturbances from the traveling particle or object have propagated into that zone yet. So that whole zone, there's no knowledge of the object yet. Okay, and so what this thing is called, this region enclosed by these two lines, it's called the Mach cone. So in fact, right now I can get rid of the rule lines again. So This is what's referred to as the Mach cone. Okay. And there's an angle here, so we can draw a dashed line that bisects the cone. And the angle here is an angle mu, okay, and that's called the Mach angle. So what is mu? Okay, well, one easy way to find out what mu is you can actually, so remember that the distance here between, say, this and the edge of the disturbance is a. We can actually drop a right angle line down to the edge of the Mach cone. And you can see that since this is traveling at basically v, so let's say that we're looking at 2 time steps from t equals 2 to t equals 3. We know that the distance that was traveled between t equals 2 to t equals 3 is v, and then the distance of that side of the triangle that went straight down to the edge of the Mach cone, that is going to be a, because that's the speed at which the disturbances travel. And so you have the Mach angle here would be opposite over hypotenuse, so sine. So we can say that the sine of the Mach angle, sine of mu, is equal to a over v, which we can also see is just 1 over the Mach number. Okay, so let's write that down. This is the Mach angle. And we might as well box this as well because you will use this definition. Okay, so hopefully that wasn't too confusing. The idea is that we have this disturbance, which is emitting one point, which is emitting 1 disturbance per second, and then we started to let it move, and we saw kind of how the disturbance fronts where they lie geometrically given that level of motion. So when we're moving faster or moving slower than the sonic speed, you can see the disturbances are getting out ahead of the object, so you have some sort of a warning of it approaching, and then you can see that when you're moving right at the sonic speed, the disturbances are piling up right where at the object's location. So basically, from the object's location forward, there's silence, and then when you start to move faster than the sonic speed, you get this zone of silence that flanks the object that's traveling, and that zone of silence will sort of cover a larger, let's say, solid angle or angular region, depending on how fast you're going. Okay, given by the Mach angle, which we defined here. Okay, so hopefully that's understandable. So that'll be the last thing that we cover today, and I wanted to. We'll conclude the lecture by thinking about this for just a second. Okay, so what does this mean? Well, in the subsonic case, like we said, the oncoming flow is alerted to the presence of the oncoming object. Okay, what does that mean? That means that the fluid can smoothly adjust to the flow around the object, and then adjust its flow to go around the object in a nice way. So like let's say that we have some, we'll just call this subsonic. Let's say that we have some sort of sphere that's traveling through a fluid, okay? And here we have that the velocity is less than the sonic speed. This is like cases that you probably saw in fluid mechanics, right? The flow lines sort of contour nicely around the object. Okay, they go around it. We have a stagnation point right here, but in general, this is sort of this nice smooth variation of flow parameters around the object, right? Because it's moving slowly enough so that the upstream particles actually know it's coming, so they have time to adjust, right? But in the supersonic case, that's not what you have. So in the supersonic case, where we have V greater than A, you have the object, and then what happens is that all the flow lines upstream of the object are parallel because they don't know what to do. They just go straight until they encounter the disturbance or the traveling object. And what happens is you get this formation of a shock. Okay, we're going to talk about shock. Shocks are the bread and butter of this whole course. Okay, we're going to talk about this in detail. But essentially what's happening here is the object is traveling so fast that the upstream flow cannot continuously deform for the object. And so what you end up with is a discontinuity in flow parameters. That's represented by a shock. Okay, and we'll talk about the details of this later. So details later on that one. But so think about that. That this, if you've ever sort of wondered what causes shocks, it's this fundamental idea that the air molecules don't have the opportunity to rearrange themselves, and so you have continuous variation of the flow parameters. But yeah, so spend some time thinking about that, and in subsequent lectures we will get into detail of shockwaves, and we'll learn about how to calculate all the way properties change across them, and how to design our supersonic systems to take all of these shock phenomena into account. Okay, so thanks for listening, and I will see you in the next lecture.